Hello everybody and welcome to part 2 of the Checkers AI tutorial. So in this video, we're actually going to be implementing the Minimax algorithm. Now the first thing I want to do though is make sure you guys are set up with the code. So please go to the description and download all of the code. So this is what it's going to look like here. I'm going to walk through it quickly just to make sure everyone's clear on how all of this stuff works. But if you want to see how you actually build all of this code, again, I already made a series on just walking through and building this checkers game. Of course, if you're interested in the AI, then just download the code and we'll go from there. But anyways, when you download the code, you'll see that there is a main.py file, there's a checkers folder, an assets folder, and some init.pys. Main.py is actually how the game is played in terms of the UI side. So this allows us to select certain pieces, move, so on and so forth. Now we're going to be modifying a few bits of this code. So the first thing I want to do is just kind of explain to you how this works. So in main.py, it's pretty simple. This is really just what is actually getting the user's input. So you can see we kind of have a main game loop here. It's checking if someone has won. If it does, it's printing the winner. And actually what we should do in here is say run equals false, which means we're going to quit the game. So this is the first addition we can make on line 27 if someone has won the game. Now, what else we see is we have game.select, game.update. Game is a class, and that represents the state of the game. So game is actually kind of like, I don't want to call it an API, but it kind of is just an API that we can use to play a game of checkers. If you go ahead and look in this class, you can see we have an update method. This simply updates the display and draws it. We have winner, we have reset, we have select, which will allow us to actually select a piece or potentially move a piece. We have the move method, we have draw valid moves, and then we have change turn. So we can use all of these things within this class, like any ones that don't have an underscore before them, we can use them. And essentially that is just kind of how we actually play checkers. So within this class, we actually create a board from this init method. A board is another class that we've set up. The board handles the state of the board, so holding all of the pieces, allowing us to check what the valid moves are. It's the actual checkers board. Whereas the game is more handling like, okay, can you move there? Can we allow the board to move over here? Whose turn is it? That's kind of what the game is handling, whereas the board is handling more of the state of the actual game, and it's less concerned with what the user's actually doing. So if we have a look here inside of board, we can see we have some stats related to how many kings are left, how many pieces are left as well, so red left and white left. We have some methods to draw the squares, so the actual checkerboard squares. We have this move method, which will actually move a piece to a certain row and column. We have get piece, which given a row and column will give us the piece that is at that row and column. We have create board, obviously this is setting up the board. We have draw, which is drawing everything, and then remove, that's obviously going to remove a piece or pieces. We have get valid moves, which given a piece will tell us all of the valid moves that this piece could move to. We have traverse left and we have traverse right, which is handling how we actually determine where we can move to. And that's it for board. Finally, we have piece. This represents one singular piece. It stores simple things like the color. If this piece is a king, its XY position. It allows us to draw it and to move it. And that is kind of the basic setup. Now we're going to concern ourselves mostly with this game and board class. We'll just need to use them because as the AI, right, we're trying to build this AI. We need to know, first of all, well, where can the AI actually move from this position? Okay, we need to have a board that we can use to score, right? So we're going to need some way to evaluate the positions. We need to figure out all of the pieces that could potentially move. So we need to actually add a few things to this code to allow that to work. We'll do that. Actually, maybe we'll do that now. Maybe we'll do that after. In fact, let's do it now. So the first thing that I want to do is I'm going to go inside of this board class. Again, go inside of here if you just downloaded the code. And what we're going to do is simply add an evaluate method. Now, the evaluate will tell us, given the state of this board, what is its score. Now, we'll use a really simple evaluation method, which is going to take into account how many kings we have and how many pieces we have. So define evaluate self. Now, this means if we have a board object, we can just call .evaluate on it. It will return to us some number, positive or negative, telling us the score of this board. Now, in the last video, I told us that to score a board, we would simply subtract the amount of white versus the amount of red. Now, we can do that if we want. So we can return self.whiteleft minus self.red, red left, like that. And that will give us a positive, negative score. White's going to be our AI. So if white has more pieces left, obviously this is going to be positive. Now that's fine, but I would like to incentivize our AI to actually try to become a king if it can. If I don't do this, it means that it's not going to prioritize moving to the end of the board. It's just going to kind of slowly move its pieces upwards. So if we actually prioritize it becoming a king, then it's more likely that we'll see a forward progression and that it actually will try to become a king, which obviously is an advantageous piece to be. So what I'm going to do is simply subtract this, and then I'm going to multiply the red kings and the white kings by a negative and positive number and add them together. So what I'm going to do is I'm going to say plus, in this case, the self.white kings left multiplied by 0.5. So that means if we have, or sorry, not white, we'll say white kings, my bad. So self.white kings multiplied by 0.5. And then we'll subtract here the self.red kings multiplied by 0.5. So what this will do is essentially just give us another value, right? So if there's more red kings than there is white kings, then obviously this will be 0 minus, this means we'll actually be subtracting whatever the amount of red kings times 0.5 is from this evaluate. Or from this score, sorry. So hopefully that makes sense, but this is what we're gonna use. Feel free to tweak this, mess around with it, make it more complex if you want. The better we make this function at evaluating the board, the better our AI is going to be. All right, now that we have that, the next thing that I need to do is actually make a method that can return to us all of the pieces of a certain color. The reason I need this is that we can simply use the board. If we have a look here, it says get valid moves to get all of the valid moves for a specific piece. But if we want to check all the moves that a possible color could make, what we need to do is determine, okay, what are all of the pieces on the board that are this color, and then check all of the valid moves for all of those pieces, right? If we have 10 pieces, all of those 10 pieces could potentially move, so we need to actually get all of those pieces. So again, don't be too concerned about this because this is code that you guys haven't written yet. I wouldn't expect you to understand it, but just a few things that we need to add. So define get underscore all underscore pieces like that. We'll put self in here and we'll say color. Now what's going to happen is we're going to pass a color in here, an RGB color, so either red, green, blue, whatever the piece color is, and we will loop through all of the pieces that we're storing in this board and return the ones that are that color. So I'm going to say pieces equals a blank list and just try to follow along here. Although this code will be in the description as well. So not only the old code, but the final new code. And I'm going to say for, in this case, row in self.board. So if we have a look here, this board has an internal representation of all of its pieces. It's actually a two-dimensional array. It looks something, say like this, where, you know, let's just imagine it was like a 3x3 checkerboard. It would have like a piece object. It would have a 0 if there wasn't anything there. It would have a piece object. It might have 0, piece, 0. So essentially, if there is a piece in that square, it stores a piece object. Otherwise, it stores a 0. We can figure out where a piece is by looking at its position in the list. In this case, this piece would be at 0, 0 because it's in the 0th row and the 0th column. This would be at 0, 1 because it is in the 0th row. This would be 1, 0 if we're going to go row column. So this would be in the first row and the 0th column. All right, so that is kind of how that works. Hopefully that makes sense, but we'll say for row in self.board, and we'll say for piece in not self in row, and we'll say if piece does not equal 0 and piece.color equals color, then pieces dot append piece return pieces. All right, so make sure I spell piece correctly or pieces correctly. Hopefully this is pretty straightforward. Again, just looping through all of the rows. For each row, we're gonna loop through all of the pieces. If the piece is not 0, we will check and see what color it is. If it is the color that we requested, we will add it to the list and we will return it. Okay, so that is, I believe, all we need for the board. We now need to go to game, and I'm just gonna add one method here because we'll need to do this. I'm going to say define get underscore board. And all we're going to do here is say self and then return self.board. Now, actually, I'll add one more thing as well. So get board is just saying, okay, we have this board object, right, that's stored here. we were going to want to get that when we actually start using the algorithm. So we'll just add a method to return that. Next, what I'm going to do is say define AI underscore move. Now, this is a bit preemptive. You're not really going to understand why we're doing this right now. But essentially, when our AI makes a move, what it's going to do is just return to us the new board after its move. So rather than saying like, oh, I'm going to move this piece here, which we could do, but that will be kind of complicated, what I'm going to do is just make it so that we can just pass a new board object to the game, and it will simply update the game with that new board object. So all we're going to say is self.board equals board, and then we're going to say self.change turn. So we'll simply change turns right here after we get this board, or after we update the board, because obviously if it's white's turn, well, we need to change it to red, and you can see that that is what this does. Okay, so now that we've done that, we're looking good. What I'm going to do is add a new folder inside of this directory, not inside of the checkers directory, sorry, but inside of the like upper level directory that I'm in, and I'm going to call this Minimax. Now inside of Minimax, I'm going to add a file. This is underscore init.py. What this is going to do is make Minimax a package, which means I can import stuff directly from this Minimax folder. Inside of here now, what I'm going to do is make a new file. I'm going to call this algorithm.py, and you can assume what's going to go in here, obviously the algorithm that we're about to write. Now I will be referencing my other screen just because this is a complicated algorithm somewhat, and I just don't want to mess it up for you guys. So I will be looking over there if you see me kind of peering to the left. Anyways, what I'm going to do is start by importing a few things. I'm going to say from copy, import deep copy. We're going to use this in a second, but what we're essentially going to do is copy the board a bunch of times. What deep copy does is we'll make a actual, it's kind of hard to say this, but you can make what's known as I think it's called a shallow copy or a deep copy. A shallow copy will simply copy the reference to a object, whereas a deep copy will copy not only the reference, but the object itself. So essentially said I did something like this, right? X equals list, Y equals X. If I modify X or Y, it will modify both of the variables. Like if I say X0 equals 1, then that means Y0 will equal 1 as well. Obviously, we don't want that when we're going to be doing this algorithm. So if we said something like Y equals deep copy of X, then what would actually happen is if I modified X or Y now, they won't modify each other. That's the basis behind deep copy, but we'll talk about that after. I'm going to import Pygame, and I think that's all I need for right now. I'm also going to define the two colors we're going to be using. So I'm going to say red equals 255.0.0. By the way, if you don't have Pygame installed on your system, you will need to install that to get this to work. I'll quickly show you how to do that. What you can do is open up your command prompt or your terminal if you're on Mac or Windows. And what you need to do is simply type pip install Pygame. If you're on Windows, this will be the command you need to run. Press enter. Obviously, you need to have Python on your system for this to work. And if you're on Mac or Linux, type pip3 install Pygame. For some reason, this doesn't work for you. I will leave videos in the description that say how to install Pygame on Mac and how to install Pygame on Windows. And I will also leave cards to them in the corner. It should be the top left or right-hand corner where you guys can have a look at those and follow along with that. Then come back, install Pygame, and be good to go. All right, so we have red. Now I'm going to say white. Now in Pygame, when we define colors, we define them with RGB. Obviously, all red, 0 green, 0 blue is going to be red, and all of the colors is white. So 255, 255, 255. Now what I'm going to do is I'm going to say define Minimax, and inside of here I'm going to say position, depth, max underscore player, and game. Now, position is going to stand for the current position that we are in. So what position will actually be is a board object. So we have boards like this, right? And what we will do is we'll pass different boards to the Minimax algorithm and say, okay, based on this board, give me the best possible board after this that I should move into as the white player or as the red player. So we have position, which stands for really the board. It's telling us, okay, this is where we are, what current position we're in. Depth is telling us, okay, how far am I making this tree? How far am I extending this tree? We're going to decrement this, and this is going to be a recursive call, which means every time we call this, the depth will decrease by 1. Next, we're going to have max player. This is going to be a Boolean value that tells us, okay, are we minimizing the value or are we maximizing the value? So if max player is true, then that means we are trying to maximize. If min player is max player's fault, we are trying to minimize. Again, that means we technically could use this AI to have the AI play against each other, white and red, which maybe we'll show later. Next, we have game. Game is the actual game object that we're going to get right from here in this main.py file. We're going to pass that to the algorithm. And what that will do is then strip out anything it needs from that and potentially draw some stuff on the screen if we want to do some visualization. All right, so the first thing to do inside of the Minimax algorithm is to determine what our depth is. Now, remember that we only evaluate a position when we reach the end of the tree. So in our previous example, we had the root node, and then we had 2 side nodes, right? And then, or 2 or 3 nodes after that. And then after all those nodes, we had other nodes, right? So it went like the red move, or it went the white move, and then the red move, and we evaluated at the red move and bubbled up those evaluations upwards. So we're only going to actually make an evaluation if the depth of our tree is at 0. So if we're looking at the last node essentially in the branch that we're on. So I'm going to say if depth equals 0 or position.winner. Now remember that if we look at board, we have this winner method that I put somewhere, maybe at the top. I think I had winner. Yeah, winner is right here. So we can check if someone has won the game. So essentially, if position.winner, we can just say it does not equal none. Then what we're going to do is return position.evaluate and position. Now I'll talk about why we're also going to return position afterwards. But the point of this is essentially to say, okay, if the depth is 0, so we're at the last node in the tree, meaning we're not going any further than this. Let's get the actual evaluation of that position. And then let's return this current position alongside of its evaluation. So we know what evaluation goes with what position. Now, when I say or position.winner does not equal none, what I'm trying to say is, well, if we've won the game, then the game is over. There's no need to continue evaluating, right? So that's what this is saying. All right, so now I'm going to say if max underscore player and else. So the reason for this, you can kind of guess, is because, well, if it is the max player, then we're going to do something different, maximize the score. Whereas if it's the min player, we're going to minimize. So these two blocks here, the if and else, will be similar. We can actually copy and paste them and change some things, but it's just because max and min. So the first thing I'm going to say is the max evaluation that I've seen so far is negative infinity. Reason for this is because whenever we check a new position, we're going to determine which one is the best. And well, if we haven't checked anything yet, then currently the best that we've seen is negative infinity, right? Meaning if we see anything else that has a score higher than negative infinity, which they all will, we'll consider that the current best until something else comes along and beats it. Next, I'm going to say best underscore path equals none. You can guess what, or actually instead of best path, let's say best move equals none. You can guess what that means. That's going to store the best move that we could make. And then we're going to say for move in get all moves, which I'm going to write in a second. This is going to be a function. What this function will do is get all of the possible moves for our current position. So we'll pass it the position. We'll pass it actually the color that we want to consider, which in this case is going to be white because the maximizing player is going to be the white player. We're just going to hard code that in there. And we will pass it the game in case, again, we want to draw anything for visualization purposes. So actually, rather than waiting before we write this, I'm going to write this now just so that the get all moves function, just so that it's clear and that we don't get too confused and then go back to it. So I'm going to say define get underscore all underscore moves. What this is going to take is a position, it's going to take a color, and it's going to take the game. Now, the point of this function is to get all of the possible moves that we could make from the current position. So that is why, again, within this board class, we just wrote that method that got all moves. I forget where I put it, but I think it was like, yeah, get all pieces. So that inside of here, we can get all of the pieces, and then we can check all of the moves for those pieces and add those into a moves list. So I'm going to say moves equals a blank list. Moves, what this list is going to store is it's going to store the new board. So it's going to look like this, board and piece. Essentially, it's going to say, okay, if we move this piece, this is what the new board will look like if we move it to a certain position. So this is the piece and this is the new board. And then we'll have a bunch of these that'll say, okay, this is, another new board. So new board, and this is a piece that we move to get that new board. So moves equals a blank list. And I'm going to say for piece in board dot get all moves, or not get all moves, sorry, get all pieces. And we just need to pass it the color. So we'll simply pass it color like that. And what this will do is get all of the pieces of that certain color. Now I'm going to say valid underscore moves equals board dot get all valid moves, or get valid underscore moves. And we'll just pass it the piece. So hopefully this is making sense. Loop through all the pieces in the board that are the certain color, get all of the valid moves for that piece on the board, and then say for move comma skip, which I'll explain in a second, in valid moves dot items like that. Now we're going to do something. So valid moves dot items is saying, okay, I want to loop through, since this is a dictionary, all of the items. Now the items is a key value pair, right? And the key value pair is going to say row column colon, and then it's going to have a list of all of the of all of the pieces that we would skip if we move to this row column. So the way that I've kind of done this is that the keys are going to say, okay, if we move this piece to this position, to this row column position, we will skip over and need to remove these pieces. That's, say, if I jumped over another piece, then there would be pieces or a piece in this list to tell me which one I need to remove if I take this move. Most of these won't have anything because most of the moves we make won't be jumping over someone else, but they potentially could be, right? So that's what we need to consider. All right, so for move skip in valid move.items. Move, again, is that row column tuple. Skip is a list of the pieces we would skip. What I'm going to say is temporary board equals deep copy board. So I need to do this, and sorry, instead of position, I'm going to call this board. It's really the same thing, but board I think is just more clear here. So we'll say board, but I'm going to deep copy the board because I'm going to be modifying this board in order to determine when I move to this position what the new board will look like. So I don't want to modify the same board. I want to make a copy of it every single time so that the next piece that I consider has a fresh board that it could potentially move to. Hopefully that makes sense, but we just can't have it be the same board. Otherwise, every time we move a piece, it will move on the same board, which means when we're running this algorithm, the board will permanently move to all of the things that we're just trying out, right? Which obviously we don't want. So now I'm going to say new board equals, and this is going to be a new method, which we'll write in a second, simulate underscore move of piece, move, and then 1 second here, we need to pass the temp board, game, and skip. Now, I'll write this method in just a second, but imagine that what this is going to do is, or we haven't written this yet, but this function, sorry, imagine what this is going to do is take the piece, take the move that we want to make, take the temporary board, and then make that move on it and return to us the new board. That's what it's doing. It's telling us, okay, if you make this move, the new board will look like this. And then we're going to store that, and we're going to put that in our moves list. So we're going to say, all right, moves.append the new board like that, and then comma the piece. So we're going to say, all right, if this piece moves to whatever move it is, then the new board will look like this. And then we'll score that board from inside of here, and we'll see which board is the best, and we'll return that, and that will be the board that we then set and technically the move that we make. So I hope that makes sense. But in here, I'm going to say return moves, and now I'm going to write the function for simulate move. So define simulate underscore move. Like that. This is going to take a piece, it's going to take a move, it's going to take a board, it's going to take game, and it's going to take skip. All right, so what we're going to do in here is simply just say, if I can look at it here, board dot move. So what I'm going to do in here is now move the piece. Now, if I go to the board method here and I have a look at move, it takes a piece and a row and column we want to move it to. So what I'm going to say is board dot move piece. And we're going to move that to the move 0, move 1. Now, the reason I have to do this is just because this is a tuple, so I just need to split it up and make it 0 and 1. So this means we'll get the row and then we'll get the column. So we'll move this piece to that row and column. And then I'll say if skip, which means, okay, if we skipped over a piece or we jumped over a piece, then board.remove skip like that, and then return this board. So return board like that. Now, technically, we don't really need to return the board. I'm just going to do it because it makes sense. We could just actually not have new board equal to this and just use the temp board inside of here, but it doesn't make a big difference, so we'll leave it like this. Okay, but that is the basics for simulate move and get all moves. So now we can move back into our Minimax algorithm. We're actually almost done, but I have to write this core algorithm part now. So inside of here, what I'm going to do is I'm going to say move, child, comma, underscore. And in fact, now that I'm thinking about it, let me just say, let me just leave move where it is actually. And let me go here and just not add piece and actually just add new board, because I'm thinking about it now and I don't really care about the piece that moved, because at least for right now, I'm not drawing it anywhere. If we do decide to draw the piece that's moving and draw a circle around it and all that, which we might do, then I will add this back. But anyways, what I'm going to do is just say new board like that. So I'm going to get rid of the list that I had and just go back to new board. All right, so new board is there. Now we're back here. And I'm going to say for move in get all moves. Now what I'm going to say is evaluation. So I would write eval, but evaluation is what I have to write, is equal to minimax of the move, the depth -1. I'm actually going to write false here. And then for the game, I'm just going to pass game again. All right, so before anyone gets confused with this, essentially what I'm saying is, okay, for every single move that I could potentially make, I want to evaluate that move. Now, how I evaluate that is I call Minimax. Minimax will, if this is the last branch in the tree, so if depth is equal to 0, it will give me that position's evaluation. If it's not, it will go through and it will do what's about to be programmed here again. So it's a recursive call. We start at the root node and then we say, okay, well, I want to consider the 2 moves I could do from here. All right, so I can go left or I can go right. Imagine those are the 2 possible moves. So from there, we branch down to those, and now it says, okay, well, we want to evaluate these. So what can I do from these? Well, I can go here, and then it says, okay, well, I want to evaluate these. What can I do from here? And then it keeps going until we reach the depth that's desired, where it starts evaluating those positions, and then they bubble up. So it says, okay, well, this is -5, this is -4, so we're going to pick -4, and then that goes back and back and back, and that's kind of how it works. I hope that makes sense. This is just kind of recursion. It's hard to explain this with this example because it's kind of complicated, but this is essentially getting an evaluation for each of the nodes that we're considering. All right, so max evaluation is going to be equal to the max of max eval and evaluation. So this is saying, all right, well, now we got our evaluation. Maybe it had to go all the way down to the left and had to check a bunch of different things, but we know how good this move is. So we're going to see, is it better than what we already have in here? If it is, we'll change that. Otherwise, it will stay the same. Then what we say is if max eval equals evaluation, we'll say the best path or the best move is equal to the current move. And what this is going to do is keep track of, okay, so if the move that we just looked at is the best one that we've seen so far, then let's set that in this variable so that we know that this is, the best board that we possibly have, or the best move that we can make. And then what I'm going to say is return the max evaluation and the best underscore path. So what this will do, imagine if I call this one time, right? I call this Minimax algorithm the first time. If it's the max player, it will go through all of this. It will determine the maximum possible move we could make and the best path and return that to me. Now, of course, that's not going to happen until we do all of these recursive calls. But after all of this stuff has finished, it's been evaluated, we will know what the best path is and we'll be able to return that from here. Now, we don't care about what the best path is when we actually are inside of here. So what I need to do is where it says Minimax is I'm just going to take Minimax of 0. The reason for this is that Minimax returns to us a position or some board as well as the value for that position or board, right? It tells us the best or the worst one depending on how we're calling it. So I'm just going to strip off the fact that it's giving me the path and just take the number. Only when I'm returning back to the caller, do I care about actually keeping the best path. So I know this is confusing. This is an advanced thing, but let's just keep going and hopefully it's somewhat making sense. So actually I'm going to copy all this now and I'm going to put it in here. And we're just going to change some of these things to say, instead of max eval, this is going to say min eval. This is going to be positive infinity because the worst that we've seen so far is positive infinity. We're going to say for move and get all moves. Instead of white, we're going to say red. And then we're going to say evaluation equals minimax of move, depth -1. Instead of false, we're going to say true. Again, the reason for this is that after we look inside of here, right, we're evaluating for the best player here. So if we're going down another depth, then we need to consider what it's going to be for the worst player. So it's like flip-flopping. So what will happen is it will start by going into this if statement. Then this will be called with false, which means we'll then go into this statement. Then say we branch even more, then this one will be called with true, which will go into this statement. So it's going back and forth between red, white, red, white to figure out the mini max, right, of whatever nodes we're considering. Okay, so, and sorry, not best path, that should say best move. And instead of best path, again, this will say best move. And now let's just change a few things. So instead of max eval, it's going to say min eval. It was the min eval of min eval and evaluation. And we'll say if the min eval equals evaluation, then the best move equals move. And we can return the best move. So, and instead of max eval, return min eval, best move. So believe it or not, this algorithm is actually finished. Now I'll show you it functioning in a second. We do actually have to still call this, but let me just run through one more high level time how all of this works. So Minimax, it takes some board, which is telling us the details about all of the pieces on there, some depth, which is telling us, okay, how many positions do I want to consider? It tells us, are we looking to maximize this score or minimize this score? And then the game. Game is relevant right now. We might use that later, which is why I kept it in, but you can remove it if you want. And then I'm going to say if depth equals 0. So if we're at the furthest down that we can go when we're considering, then what we'll do is say position.evaluate and return the position. Or, of course, in the situation where someone has won, there's no more further to go down. We've won the game, so we just return this position and the evaluation. Now, the reason I'm returning both is, again, because just the way this works, we need to return two things so that we can get not only the best possible number, right? So we get, the highest number, the lowest number, but we also get what position corresponds with that so we know where to move to. Anyways, it gives us that. And then in the situation where the depth is not 0 or someone is not 1, we say, okay, are we maximizing or minimizing? For maximizing, we run this. This says, all right, the max eval starts at -infinity. The best move yet, we don't know. And we say for move and get all moves. First, we get all of the moves related to the current position for the color white, which is the maximizing player. Then what we do is we loop through all of these moves and we evaluate these moves with the Minimax algorithm. So we say, okay, well, if we're only at depth, say 2, and we need to go to depth 0, then let's check what the minimax of this move is, right? It's recursive. So then we call this minimax, and we would go and we would repeat this process, and we would then, in this case, go to the minimizing player if the depth was not 0. Then the minimizing player would do its thing. It would return to us what the min evaluation is. It might potentially have to call minimax again. And then all of a sudden we have an evaluation for whatever move we could potentially make. Now we check, okay, is this evaluation better than what we currently have? If it is, we set it and we set the best move. If it's not, we keep going until we've considered all of the possible moves. Works the exact same thing for min evaluation, and hopefully that makes sense. I think simulate move and get all moves are good enough, and let's just make sure valid moves is spelt correctly. Okay, a lot of talking. Sorry, I know this is complex. I'm trying my best to explain. Now let's go into the main loop, and I'm going to show you how we can do this. So right now, the game currently works like we can select a piece, we can move a piece, blah, blah, blah. Now, if we just run this right now, none of our algorithm, oh, it's telling me invalid syntax, 1 second. Our algorithm obviously isn't going to run because we haven't called it. And right now you just play 2 players. So what I'm going to do is simply add a thing inside of here that says if game dot, I think, do I have get turn? No, I don't. I can just say if game dot turn equals white, which means the computer, then let's call the Minimax algorithm on the current board. So let me start by importing it. I'm gonna say from, and remember Minimax is in its own folder. So I say from Minimax dot algorithm. Did I call it algorithms? No, it should just be algorithm. Import Minimax. All right, so now we have that. So inside of here, I'm gonna say Minimax, and I'll actually say the new underscore board. I'll say value comma new underscore board equals the Minimax of the game dot get board, because we want to get the board from this game, the color, which is white, and then we'll just pass the game object. All right, so value new board. What is it saying here? Undefined variable white. Okay, let me just import white from constants. You guys can just add this right here, comma white, and then that should fix it for you. All right, so value comma new board equals Minimax of game.getBoard white game. Now what we're gonna do is say, okay, game.ai move new board. What that's gonna do, right, is it's gonna say, okay, well, the AI has moved, so let's update the new board to be whatever board this is. And then that will actually change the turn for us, and then it will allow the red player to move again. Okay, I know this is a lot, but let me just test this and see if I messed anything up. And what did we get? Minimax missing one required positional argument game. Interesting. So let me go back to Minimax and see what we've done. I forgot to add the depth. Sorry guys. So what we need to do is say game.getBoard, and we need to pass a depth. I'm going to pass a depth of 3. You're going to notice if you're on a slow machine, this will take a while. Go up as high as you want with the depth, but that means the higher the depth you go, technically the better the AI will be, but the longer it will take to run. So, you know, you can kind of pick your poison on what you want there. But let me go and move, and whoa, okay, we got some crazy thing happening here. So let me just quickly check what's going wrong. Notice that a bunch of stuff just moved when really only one thing should move. All right, so I've realized the error. It's kind of a weird one. It's also just based on how I program this game. So my apologies to you guys that we're gonna have to make this strange fix. But essentially the problem that was happening is that these pieces are not copied, but the board is copied. So what's happening is when I pass piece in here to simulate move, and we move this piece, it's changing the actual piece on the board. So the board itself isn't changing, but it's changing the piece that's associated with the board. So what I need to do is get the new piece that's copied inside of this board and use that instead to pass here. So I'm gonna say temp underscore piece equals, I'm not gonna deep copy that piece, but what I'm actually gonna do is say temp underscore board dot get piece, because this will copy all of the pieces that are stored within the board automatically. And what I'll do is I'll say piece.row, piece.call. And then I'll pass a new piece here, and now it'll work. But, or sorry, not new piece, temp piece. But what this is saying essentially is, okay, from this new board, get the piece that is in the same position as where this piece would be. And that should work. I don't think we'll have any errors with that, but let me run this and just make sure. Okay, so I've just been playing against this for a minute to make sure everything's working. I think it's all working properly. The white piece has actually managed to get a king piece. I'm not really playing, the most properly ever, but now we're running into an issue where it just keeps going in between king, not king, king, not king. Maybe it just doesn't want to actually move. So let me see what happens if I open myself up to be jumped. I mean, it's still moving like that. Oh, and now it decides to move there. So maybe the AI is just way smarter than I think, and he actually is moving in some of an accurate place. All right, so I've been messing around with it. It seems to work fine. I mean, you guys can play with it yourself and see if there's any bugs. But what I'm gonna do now is just show you how we can draw what's being considered by the AI. And I'll actually make the depth 4 and just show you the difference in speed. So now if I run this and I move, we can see that it takes significantly longer to actually make the move. Before it was happening pretty much instantly, at least I'm not sure what you guys saw in the video, but it was going pretty quickly. Now it's actually taking more time before it's moving. And if I change this to 5, I almost guarantee it's gonna take a really long time to move. So let's see, I move it there, and look at this. It's just thinking. I can't even move it, just frozen, right? Because adding that one extra layer makes it take so much longer. So it eventually moved, and that was the move it decided on, but it had to consider so much more. So it will be a better AI, but you'll have to tell your players, hey, you're gonna have to wait for it because, well, it's gonna have to take some time to think. Now we could add that optimization technique. As I mentioned, I'm not going to do that, but just wanted to be clear. All right, so now let's go to algorithm. And since we have game inside of here, what we can do is actually start drawing some stuff related to the moves that the AI is considering. And I'll add some like time.sleeps in this so that we can see kind of what it's actually looking at. So I'm just going to make a function here. I'm going to say define draw underscore moves. I'm going to take a game, a board, board, and a piece. Now what I'm going to do is I'm going to say valid underscore moves equals board.get underscore valid moves for the piece. This is kind of redundant. We've done this before, but anyways, it's fine. It's just for the drawing purposes. I'm going to say board.draw, and I'm going to simply pass the game.window to it. I'm just going to go through all this and then I'll talk about what it's doing. I'm going to say pygame.draw.circle, and I'm going to say game.win. I'm going to say 0, 255, 0. I'm going to say piece.x, piece.y, and then I'm going to say 50, 5. Now, what I just did is draw a green circle around the piece. So we're going to pass to this draw moves a piece, a board, and the game, and it's going to draw all the valid moves for that piece just so that we can see it and make sure we're not running into any like critical errors, and you can kind of visualize how this is working. Next, I'm going to say game.draw underscore valid underscore moves. I think that's what I called it. And I'm going to say valid underscore moves dot keys. And then finally, I'm going to say pygame dot display dot update, and then pygame dot time dot sleep. And I think I passed milliseconds into this, so I'm going to pass 100, which means we'll sleep for 100 milliseconds. Now, I know I just like rushed through that. Valid moves gets all the valid moves for a piece. Board.draw redraws the board on the game window. So game.win is just the window that we can draw on. Pygame.draw.circle, draw it on the game window. Color green, that's what 0, 2, 55, 0 is. Piece.x, piece.y, this is the middle of the circle. 50, this is the radius. 5, this is the thickness of the outline of the circle. Then game.draw valid moves. This will draw all of the valid moves. The reason I got keys is again because our valid moves look something like this. We have like 4, 5, comma, some piece object in here. So we need to make sure that we just pass the actual row call. We're not passing that piece object to confuse this method. Next, pygame.display.update, that will update the display. Pygame.time.sleep, this will sleep it for 0.1 seconds so that we can actually see it being drawn. Let's run this and see what's happening. All right, so when I do that, nothing happens because I didn't call that method or that function. So we need to call that. I need to remember where I actually end up calling this from because I can't remember, but I think I do it inside of the get all moves. That would seem to make sense. Simulate move, get all move. Yes, let's do it inside of here. All right, so I'm going to say draw underscore moves, and I'm going to draw that with the game, the board, and the piece. Not important that I pass that temporary board or that other piece. We're not going to see them actually moving. We're just going to see them considering these specific moves. All right, so let's now do this. All right, main.py, run, and let's go ahead and move. And what is happening? Pygame has no attribute sleep. Maybe I messed something up. Pygame.time.sleep, is that not an attribute? Okay, you know what, guys? I don't know why that one's not working. Usually that's something. Sorry, it's not sleep, it's delay. Pygame.time.delay. All right, that's what it should be. Okay, let's look at this now. And we can see that it's going quite quickly, but it's showing us pretty much what it's considering. And you can kind of see the pieces moving as it's simulating everything as we go through. So this is really what's happening kind of in the back end is it's moving all these pieces. It's checking, okay, if I move in this position, what's the score? Is this the best position? Should I move here? Should I move there? And notice that it's not only considering the white, it's considering the red because it has to consider all of our moves based on all of its potential moves. So this is obviously going to take a long time to run through and draw everything. What I'm going to do is just quit out of this game. So close the program. It's not responding just because it's not threaded, so I can't do that. And what I'm going to do is remove this delay, and you're just going to watch it literally like zip through, which I think is kind of funny to see. So now what I'll do is go like that, And it just literally spams the screen showing us, okay, we're thinking about where we're going. And there you go. The decided move was to go from here to here. Now, of course, you guys can add stuff to this, play around with it, but that is all I'm going to do for this tutorial. If you guys have any questions, as always, please leave them down below, but that is how you make a Checkers AI using the Minimax algorithm. I apologize if any of this went over your head. It is difficult to explain this stuff because it is, somewhat complicated stuff, right? This is not the easiest thing in the world. Anyways, if you guys enjoyed, make sure to leave a like, subscribe to the channel, and of course, I will see you again in another Python tutorial.